Okay, welcome everybody. So today we are going to continue our discussion on data structures and algorithms. Today we are going to discuss a very interesting data structure called heaps. So in the last class we had seen priority queues, right? Priority queue is basically a queue in which people or the nodes or the entries, they also have a priority index. Let's say in a hospital there is a queue, but then you see an emergency case, then that emergency case gets the priority and the doctor attends to that case first, right? So similarly you can have a different priority number for every uh, node, and then depending on their priority index they will be catered to, which means it is possible that somebody comes at the end, but still, since that node has got the highest priority, it will be attended to first. Okay. So there is a way to implement priority queue. Priority queue is basically, like I told in the last class, it's a black box. How you implement it depends on you. So there is one possible way to implement it, that is with the help of heaps. So heaps are basically a data structure and an abstract data type which is used for uh, various things, including to implement priority queues. Okay, so what is a heap? So, so heap has a property. It is a kind of you can say it is a connected. All the nodes are connected, and it's like a tree, but it has a property. A tree is basically, if you remember the properties of tree has got a root node, and then it has a hierarchy of parent-child relationships, where a parent can have multiple children, but a child can have only one parent. A child cannot have multiple parents, right? That was a tree. Now this heap also has that same property, but on top of it, it has one more property, and that property is that let us say this is one kind of heap called a min heap. In the min heap, the minimum value is at the top and the maximum values are at the bottom. Oh, this is just a casual way of saying it. More precisely, the parent is always greater than or equal to the child. It could be equal to also, in case your heap allows same entries repeated, then parent will be greater than or equal to the child, and that is called max heap. And in the min heap, the parent is always less than or equal to the child. So this, what I have shown here, is the mean heap. So you can imagine it, it's a heap in which the bottom entries are all heavy, or the larger values, and then as you go towards the top, they become lighter and lighter, or they become smaller and smaller. And but the max heap will be the opposite. Basically the lower values will be small values, and as you go towards the top you get larger and larger values. So precisely the definition is this: the parent is less than or equal to the child in a min heap. Okay, and these two are interconvertible, right? If I replace every entry with a negative sign, then the min heap will become max heap. Basically the same data structure can be used, or the same program or same function can be used to implement both min or max, just by, you can take a negative sign, or basically just invert the polarity, or um, the comparison property, right? This is a comparison property. Okay, now what are the advantages of heap? So as I told you in the previous classes also, every data structure gives us uh, uh, means gives us a way of organizing data, and it has its own pros and cons. So you want some operations to be very fast, while at the cost of others. So every data set has very fast operations. Some operations are very fast, but other operations could be slow. So in a heap, what is the advantage? So one operation which is very fast is adding and removing of elements, especially from the top. If I'm adding a new element, that can be okay. A new element is added and that is very fast. And then if I want to remove the the topmost entry. For example, imagine a priority queue where you want to uh, remove the next dequeue the next entry, right? So that is very fast in a heap. So if you want to remove the root node, that is very fast because you can rearrange it quickly so that again the heap is formed. Uh, and when a new element is added, you can rearrange it quickly so that the heap is formed or the heap property is maintained. Okay, so there is some terminology. So a binary heap. So as the name suggests, binary means there are two children at the most for every parent. So let's say this is a root node, it has got two children. This is another parent node, it has got only one child. This has got two children, this has got two children, and this has got no children, it's a leaf node, right? Uh, so in this way, you can see the heap property, heap invariant. So what is heap invariant? It is this property. This property is called heap property or heap invariant, that always the parent is smaller than the child in case of min heap. I will be using min heap because both are kind of dual of each other. What do you say? Both are equivalent. So I will just go with min heap for our examples here. Okay, okay, let me go back. Yeah, so binary heap is basically every parent can have at most two children or one children or no child, that is all right. Okay, and then a complete binary tree. A complete binary tree means all the levels are filled, all the levels are filled except the last level, or where all the even in the last level all the nodes which are filled are towards the left only. So you see here in this example, uh, this node is unfilled and this node is unfilled, right? These two nodes do not exist because there is no data there. So what I mean to say is that in a complete binary tree, so binary properties there are two children for each parent, and the completeness means like all the levels are complete except the last level possibly. Uh, but then even at the last level, all the filled nodes will be towards the towards the left only. That is a complete binary tree. Okay.
That is like the maximum thing. Matlab, that is the maximum compromise on a complete binary tree. That if at all the nodes are absent, it can only be on the right side. That's what you're saying, right?
Yes, yes. So tell me now, is this a complete binary tree?
No.
No.
Okay, good. Why? Because this node is missing, which is at a higher level. This is not at the lowest level, right? Lowest level is this. If you call this as level 0, level 1, level 2, level 3, then level 2 has missing nodes. And even level 3 should have all the filled nodes towards the left. So this is not a complete binary tree. But this one is a complete binary tree. Okay, let's go to the next. Okay, now there are some exercises for you. Take out your pen and paper if you want. Okay, the question is uh, number of nodes at level L. If there are total capital N nodes, okay, no, just tell me. Okay, let us say that I have a complete binary tree. Now tell me at level L, how many nodes are there? For example, I ask you at the level 0, how many nodes are there? You will say only one node. Only one node is possible, right? At level 1, how many nodes are possible? You will say only two nodes are possible. At level 3, 4, like that. If I ask you in general at level L, how many nodes are possible? Write on the chat window your answer. Please write on the chat window. I have it open in front of me. Okay, so people are writing 2 to the power L. Very good. Yes, correct answer. So if my L is starting from 0, level 1, level 2, level 3, then each level has at the most 2 to the power L nodes. You can verify. Okay, so the answer to this question or this Let me write it with light blue. 2 to the power L. Okay, good. Now tell me, if number of levels is capital L, right? Like this, there are 4 levels here, 0 to 3. What is the maximum number of nodes that are possible in a complete binary heap? What is the maximum number of nodes possible in a complete binary tree or binary heap? Okay, you have to give me the answer. Okay, so Jan says 2 to the power L minus 1. Okay, 2 to the power L minus 1. Yeah, that's the correct answer. 2 to the power, okay, how do you arrive at this answer? So you will say, okay, I have to go to level capital L. So basically my L goes from 0 to L minus 1, right? So the what number of nodes in the first level will be 2 to the power 0, plus in the in the level L equal to 1, it will be 2 to the power 1, plus so on, plus 2 to the power L minus 1. So this is a GP, right? Geometric progression. What is the sum of this GP? This is equal to uh, what is it? The common ratio to the power number of terms. How many terms are there? Total capital L terms are there. Minus 1 upon common ratio minus 1. Right? So 2 to the power L minus 1 is the right answer. Okay. Now tell me, the next question is, if number of nodes is small n, okay, if there are, I have small n number of nodes, then tell me how many completely filled levels will be there. If I have, let's say, 4 nodes, then tell me how many levels are completely filled. You will say, okay, this is level 0 is completely filled, level 1 is completely filled, and then 3 and 4, we stop here, right? Oh, so sorry, yeah. Basically, when I say 4 nodes, it means it goes from 0 to 3. Okay, I reached here. So I have 2 levels which are completely filled, and the third level is getting filled now. Okay, so tell me, in general, if I have small n number of nodes going from 0 to n minus 1, what is the number of completely filled levels? What is the number of completely filled levels? Okay, I'm getting some good answers. Okay, Manoj has almost given the answer, but something is missing. Maybe somebody can complete it. Okay, many many people have replied. Thank you for your replies. Yes. Okay. So okay, I don't know how have you computed, but yes, I can tell you how I computed this. So I will say this is equal to. So generally, I from here I know my n small n is basically equal to 2 to the power L minus 1. This is the maximum number, right? If my all the things are filled, but if something is unfilled, then it will be number of levels is L minus 1. Right? Okay, so what I will say, what I will do is I will say n plus 1 log 2. This is equal to capital L. Uh, this is equal to capital L, means I have reached up till here. But if something is less than this, I will just take a my L will be L minus 1. So I will just take a floor of this, right? So this answer is this log 2 n plus 1 and floor of this. Am I right? Floor of log to the base 2 n plus 1. Yeah, I see many of you have given the right answer. Good. Now, and the next part is basically the next node goes to the level. So instead of the floor, you take the ceiling, right? Uh, yeah, basically that's the same thing. Floor of something plus 1. Oh, okay, actually, you are correct. Floor of something plus 1 is a better answer. Just make it L plus 1, because to verify it, let us take 14. If I take my n is 15, basically I'm here. If my n is 15, then log 2 16. 16 means log 2 is how much? 4 to the power 4 is 16, so it's 4. So my capital L will be 5, and 0 1 2 3. Oh, okay. I'm sorry, the level number will be fifth level, but the index will be 5, so please adjust for that accordingly, right? So the index is different from total number of levels. Okay, then now next question is even little more tricky. Tell me, what are the node indices at level L? At any level L, what are the indices of the node? For example, I say at level 0, the index is 0 only. At level 1, the indices are 1, comma 2. At level 3, the indices are 3 to 6. At level, sorry, L equal to 2. L equal to 3, the indices are 7 to 14. So can you tell me what are the node indices at level small l in general? What are the node indices? Yeah, somebody says 2 to the power L minus 1 plus 1 to 2 to the power L. Okay, you can verify it. Let's say my small L is 0. So it becomes 2 to the power minus 1 plus 1. Sorry, L is 0. Okay, this does not work for L equal to 0. So this formula has to be revised a bit.
So I have one doubt over here.
Yeah.
So this n is equal to 2 raised to capital L minus 1. In this capital L has to be the number of levels, right?
Yeah.
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 So in this log of n plus 1 base 2 floor, that will give you the number of levels. But if I put 14 over there, I'm getting 3. It should give me 4, right?
Mhm. If you put 14 over here, it gives me
It gives me 3, right? You should get 4
if you put 14 in the
in
uh,
this formula.
if you
So
put
log,
small n, okay, if you put small n equal to 14.
yeah, exactly. So it will become log of 15 to the base 2, which will be somewhere between 3 and 4. And then you take the floor, you will get 3. So the number of levels you will get 3, but actually it is 4, right?
No, actually this is 3 because we are
No,
starting from level 0.
1 2 3 total
No, that's what
levels
I.
are completely filled.
So that's what I confirmed from you. You were saying that the number, the capital L is the number of levels, and not the index of the level, because in the previous formula we wrote n is equal to 2 raised to capital L minus 1, where capital L was the number of levels.
Yes, yes.
So we should get capital L is equal to 4, right?
For
No, no.
capital L equals to 4, you
If
need to
your
fill n equal
small
to
n is
15.
14, if your small n is 14, right? Then you are here 13 nodes, right? So how many totally filled levels are there? One, two, three. Three levels are totally filled. Fourth one is being filled,
Hmm.
right? If your n is equal to 3, then your capital L,
Okay, okay.
I will say
Hmm.
filled,
Okay. So I got confused with the index of the node and the number of nodes.
Yeah.
It's
Please,
actually different.
this is I have used a Python convention here. Python uses number of entries and index of entries, so the same convention I have used. Okay. Okay. Next, can somebody answer this question? Node indices at level L. Okay. Okay. Let me give the answer. All the answers are here. Oh, I have not filled the answer here. Okay, it is for you to decide. Okay, no, okay, I think I deliberately left it. I thought I will give it as an exercise, but it's all right. So, okay, but these parts you have already solved. Only this part is left. Okay, we can do it, no problem. So, if you want, it is node indices. So, let us say I am at level L. So, at level, let's say at this level, then I know how many nodes are there at the level L minus 1. Number of, just a minute. Okay, maximum number of nodes. So basically we have to find the maximum number of nodes in the previous level. So this will be 2 to the power. I'm at level L. So previously there are L levels, L minus 1. Okay, this, sorry. And this is the, okay, so the first node will be this plus 1, right? 2 to the power L minus 1. Okay, this is index, so it is okay, minus 1. And then it will go on up to how many nodes are there at this level. So this will be 2 to the power L plus 1 minus 1. And then again a minus 1. Am I right? So okay, let us verify this. Let us say at the level 0, 1. Let us say at the level 1, at L equal to 1, this will be 1. So 2 to the power, this is 1. Okay, let us say at L equal to 1, this will be 1, 2. L is 1, 2 to the power 2 is 4. 4 minus 1 is 3. 3 minus 1 is 2. Okay, this one works. At L equal to 2, 2 to the power 2 is 4 minus 1 is 3, 3, 2. 2 to the power, how much? 3. 2 to the power 3 is 8. 8 minus 2 is 6. Okay, this formula works. And this works for L equal to 0 as well, actually. At L equal to 0, this will be 2 to the power 0 minus 1. 1 minus 1 is 1. Oh, sorry. 1 minus 1 is 0. 0, 2. 2 to the power 0 plus 1, 2 to the power 1 is 2, 2 minus 2 is 0, 0 to 0. Yeah, it's the same formula works for all the levels. Okay, so fine. So this is the answer anyways. Okay, let's go to some, okay, I think you did an interesting exercise. Now let's look at uh, the an algorithm to add an element to a heap. Okay, so you got a heap. So first tell me, is it a heap? What kind of heap is this?
Min heap.
Very good, thank you. So this is a min heap, which means the small values are on the top. The node is the smallest, and then all the children are larger and larger. Okay, so this is a min heap. I want to insert a new element. That element is 1. Let us say I want to insert a 1 into this, right? How do I insert it in a way that my heap structure is maintained? My heap invariant or my heap property is maintained. So how will I do it? I will, okay, so the way is, uh, if I do it directly, if I put 1 here, and I don't know what to do with the 5 6, so the whole structure will collapse, right? I know the 1 has to come at the top because it's the smallest entry, but how do I do it? Okay, so there is an efficient algorithm which basically reduces the complexity of the entire operation. Okay, so this is how we do it. So we add the element at the next empty node. This is a complete binary heap, right? This is a complete binary heap. So the next empty node, compared with this previous image. So the next entry node will be here, the blank. So you add one there, and then you know that the heap property is not maintained, right? Because this parent is larger than the child. This is not good, because my min heap property is that my child should be should be larger than the parent. Okay, so this what do I do is I will do this operation is called bubbling up or sifting up. So imagine that this is a glass of water, because in the water the lighter things have to go up, heavier things have to sink down. So this is like a lighter bubble, and it will bubble up and finally reach here, right? You can see the analogy of bubbling up when you compare it with a glass of water or some beverage. What is the meaning of bubbling up? You basically swap. So 1 and 7, the heap property is not maintained. Okay, just swap them, then it is maintained, right? It's a binary property. So see, I have swapped now. So 7 came to the child node, 1 came to the parent node. Okay, now again check. Now this 1 is the bubble. So it compare it with the new parent now. Again, the heap property is violated. So I will again swap. Okay, so again, I swapped it. 6 came below, 1 came up. Now again, who is my new parent? 5 is the new parent. Okay, compare with with the 5 thing. So again, swap. Now see, now 1 has reached the top, and if I see the parent of 1, whether the heap property is maintained or not, in this case, the 1 is the root. So yes, this is definitely maintained. Now you check, is this a heap now? Is it a heap now? Yes. Good. So you can see now this is a heap. So how much, what is the complexity of this entire operation? What is the complexity of this entire operation in the worst case, let us say? It will be equal
Login.
to the number of levels, right? Because when you insert a new node, let's say 1 is the new node, it has to at most do uh, the number of operations is equal to the number of levels. And what is the number of levels? It's of the order of log to the base 2 n, right? You remember we have computed it. See, what is the uh, number of levels? Okay, number of levels. Where is it? If the number of nodes is n, then the number of levels is log n, of the order of log n, right? So that's what that this complexity is, of the order of log n. Okay, now in this heap, insert a new element 13. What will happen? If I want to insert another element called 13, how will the same thing will happen? I will add 13 at the bottom, at the next unfilled node, right? In the complete binary heap. And then I will do the bubbling up operation, where this 13 will be compared with the parent, and I see that the invariant property is violated. So I will do the swap. Oh, what happened? Sorry. So I will do the swap. And now the heap property is maintained. If I compare with the parent now, the heap property is maintained. So I need not swap again, right? So this is how I am adding a new element to the heap. Is this clear? Do you have any questions? So you can see that this is an efficient data structure in which my uh, uh, adding of new entries is very efficient.
Excuse
Now,
me, sir.
pardon?
Sir, how is it decided where the new element will be added initially?
Okay, in the next unfilled node, it's a complete binary tree. The property of complete binary tree is that, or complete binary heap is that all the levels are completely filled. The last level is at most unfilled. And if it is unfilled, all the filled nodes are towards the left, unfilled nodes are towards the right. So when you see here, what is the next unfilled node? It is basically this. Because this was there was no space, so I just expanded it a bit. This was the next unfilled node, right? And what is the next unfilled node to this? That will be this one, right?
So we didn't follow this in the previous example, right? When we were adding one.
We followed this. I will show you again. Okay, this was the
Yeah, okay, yes.
original heap. And where do we add one now? What is the next unfilled node? Where is my pen? Okay, it's here. So the next unfilled node is this one. If you see, here is where we
Sir,
added.
so do we,
Pardon?
sir, so do we add the element, keep the heap in terms of levels, or do we keep the heap in terms of like pointers or something?
I Please
Because
repeat. There
in
was
terms
some
of
noise.
pointers, then finding the next unfilled node according.
Okay, I'm not able to hear. There is a connection loss from your side. Ali?
So could you hear my question?
No. Can you please write on the chat window? Please write your question on the chat window. That will be more efficient because there is some.
So now the so now the so now the connection is better, I guess.
Okay.
So what I was saying is that if the heap is kept in terms of levels, then fine, we can find out the next element where the next element has to be added very easily. But if it's kept in terms of pointers, then it will be kind of difficult, right?
Yeah. Good question. So we will come to this question when we discuss the implementation of heaps. Okay. I will discuss that in a bit. Just give me some time. Okay. Okay, so here we were, we added 13 and in this way, bubbling up was done. Now, how do we remove elements? So, okay, removing elements from the root is called polling. Polling is just like dequeuing, right? You had dequeuing in the priority queue, means whoever is the person in the front, that has to be removed. And here, because of priority, you rearrange the queue so that the top priority person is in the front always, right? So this is depolling. This is dequeuing or polling. That basically polling means removing the root. Root is the next entry whom you are attending. Okay, now if you are given the command poll, how will you remove this? You have to remove it and again restructure your heap so that the heap invariant is maintained. Okay, so you can notice here that this heap it allows multiple entries with the same value, multiple nodes with the same value, right? Okay, so this is a heap. Okay, you can see all the parents are smaller than the children. The value is smaller than the children. Now I want to do the polling. What do I do? So this one, the top root, this one I remove. And I have to fill this empty node, right, to maintain the complete tree, complete heap. So what I will do is I will take the last entry. When I say last entry means the rightmost entry of the final level of the last level, the rightmost entry of the last level. This I remove from the sorry, this I remove and move it to the root. I swap it, I mean, or I replace the root with this entry. I remove this entry and I put this in the root. Okay, and then what do I do? I have a 10 on the top. Now what do I do? Is it a heap? If I move 10 here, is it a heap then?
No, sir.
No, right? Because your um, root is a very large number and it is larger than the children. So that is not a min heap. So what do I do in that case? I have to again do the bubbling operation, right? The in this now the bubbling will be in the opposite direction, that the heavier element has to sink down, right? The heavier element will sink down and reach the bottom. So it's called bubbling down or sinking down. So sinking or bubbling down. So now bubble down to maintain the heap property. So what does it mean? It means swap with the smaller child. So let us say I have a 10 here. It has to sink. It has you swap it with the smaller child. I swap it with 1, right? And 10 has reached here. And then I will further go down. This bubble has to go reach the bottom, or this stone has to sink at the bottom. Now tell me, why are we replacing with the smaller child, or why are we swapping with the smaller child and not the larger child? Right on the chat window. Why are we swapping with the smaller child and not the larger child? Or why not with any child? Yes. So simple answer is the heap property will not be maintained if if I replace with larger child, then larger will go to the top, and then again it is disrupting because these two earlier they were siblings, but now this becomes the parent, then it conflicts. So that is why you replace with the smaller child. Okay. Now this 10 has reached here. Now 10 has to further bubble down or sift down or sink down. So where will it go? Now both the children have same values. Will it go to this one or this one? So in this case, whenever there is a conflict, like whenever both children have same values, then you just by convention you take the left one, right, and replace with the or swap with the left child. So you swap with the left child. Now you have reached here, and again the heap invariant is maintained or not maintained. Is it maintained or not maintained now?
Not maintained.
Not maintained, yeah, because this is a lighter or this is a smaller value. This has to go up. So okay, so then the next is you. Now it is maintained. Now the heap invariant is maintained. Okay, so this is bubbling down or sifting down or sinking down. So now you tell me what is the complexity of this operation, the polling operation. What is the complexity? What is the complexity? O log n, right? O log n. Big O notation, O log n. Why log n? Because it is again the number of levels, right? I have to compare, I have to do the number of operations is proportional to the number of levels, which is of the order of log n, where n is the number of nodes. Okay, so now another operation which is possible, removing a given element. If I ask you, can you remove, this is a heap, can you remove 12 from this heap? Just any arbitrary entry. Can you remove 6 from this heap? Can you remove 12 from this heap? I'm not telling you what is the node index. I'm just asking you, remove the node which has the value 12, right? Just like you go to a hospital and you ask the receptionist, is there Mr. X in your queue? If he's there, then just remove him or her. Okay, so that is the operation needed. So you have to remove 12 from this heap. What will you do? So first thing you will do is you will search for the given value. Is that value there in our heap? So you will search for Mr. 12 or 12, and then you found it here. So how will you search? You will do a linear search starting from the root. You will check here. Is it 12? No. Go down because you know you are in an increasing order. So okay, you go down. Is it here? No, not here. Go here, not here. Go here, not here. Here, not here. Here, not here. Here, not here. Not here. Yes, found it. And in case you didn't find it, you will just say, oh no, it is not there. But here you found it, so now you have to remove it. If I remove it, is the heap invariant destroyed? Yes or no? If I remove 12, is the heap invariant destroyed?
No.
Yes, it is not destroyed. Uh, then that is it. Then do we need to do anything else? Is there some property which is violated? If I remove 12,
No.
Leftmost element should be filled.
yeah. So it is the completeness property is violated. Then this tree, this heap will not be a complete binary heap. So to maintain the heap property, I have to do again some rearrangement. And how will I do that? So what I do is I will remove this 12 for sure, but then I will remove this 12, but I will put this last entry and I will put it here. The last entry I bring here, right? The last node will occupy this empty position. Now I have a 3 here. Now is the invariant property maintained or not? The heap invariant is maintained or not?
No.
No, it is not maintained because the parent is larger than the child, right? Okay, so what do I do? What do I do?
Swap.
Bubbling up.
Bubbling up, very good. So this is a lighter air bubble which is trapped here. It has to bubble up and go as far as possible. So what do I do? I will, okay, I have not shown the exact steps. So you replace 3 and 8, swap 3 and 8, and then 3 is here, 8 is here. So then this 3 is compared with its parent, 5. Then again it will again swap. 3 will come here, 5 will come here. So it will be 3, 5, 8. That's what is shown here. 3, 5, 8. Okay. So this was, let us do one more example of removing a given element. Okay. Now remove 3 from this heap. Remove 3 from this heap. How do you remove 3? So first of all, you do a linear search starting from the root. Do we have a 3 in this heap? Does it have a 3? Answer is no, this is not 3. Go to this one. Is it 3? Yes, it is 3. Okay, so let us remove this. Now if I remove this, then it will not be a tree anymore because these will become, they will have no parent then. So this is removed. What do? I will bring the last element and put it here, right? Replace with the last node. This is my last node, 15. So basically this 15 will come here. And this will go away. Right? Now what do I do? Now once my 15 reaches here, then what do I do?
Bubble down.
Yes. So what will I do? Should I bubble up or should I bubble down?
Bubble down. Bubble down.
Okay. Yeah. In this case, it will bubble down. So I have to check for both the possibilities. Does it have to go up or down? So you check whether the parent is smaller. The answer is yes, the parent is smaller. So on this side, the heap invariant is maintained. Now let us check the children. Are the children larger than this? The answer is no. So, okay, let me sink down. Let me bubble down. So then this 15 will come down. Where will it go? It will go to the smallest entry. So it will replace with 5. And then it will get replaced with 8. So it will become 5 here, 8 here, and then 15 here. That's what, 5 here, 8 here, and then 15 here. Okay, so this is what is... okay, so now you know how to remove an element from a heap. And what is the complexity? Again, log n of the order O log n, right? Okay, now let us come to the implementation part. How do you implement a heap? Okay. Now, any complete tree.
Sir, excuse me.
Pardon?
Sir, search is ON, right?
Search is ON. Yes. Yes.
So the complexity isn't log n.
Yes. Very good. So the complexity of removal operation. What is the uh, complexity of the removal operation?
ON.
Yes, ON. So it is, if you see, you do first ON search plus bubbling up, which is of the order of log n. But you know, in the big O notation, the heavier entry remains, and the lighter entries, or the entries which don't increase that fast, they get eliminated. So the deciding term remains is ON. So here the removal operation, or in general the search operation, is very inefficient with this data structure. But there is a way to improve even that. We will see it in a while. Okay, now the implementation part. How do we implement a heap? A heap can be implemented with an array. Okay, a complete binary heap or a complete heap. It can be binary, tertiary, binary, ternary, quaternary, any kind of heap. But if it is a complete heap, it can be implemented with an array. So how is it so? You see the indices of this complete heap is 0, 1, 2, 3, 4, 5, 6. And same thing I can maintain in a linear array, right? So, okay, let me ask you some questions here. Okay, tell me, if I am here, let me use some red pen. If I'm here, if my, okay, for node index n, what are my, what are the indices of my child node?
1 and 2.
No, for a general n. For a general n, forget the linear implementation for time being. Just tell me, for any given node n, what are the indices of the children? For example, here my n is 1, the children are 3 and 4. Here my n is 2, children are 5 and 6. So tell me, in general,
2n plus 1, 2n plus 2.
okay, so very good answer. The answer is 2n plus 1 comma 2n plus 2. Okay, so basically I multiply with 2 to go to the next level, right? You know that it is kind of GP, the level, the nodes versus levels, it is like a GP. So to go to the next level, you have to multiply with 2, and then plus 1 and plus 2 are the two indices. So this is 2n plus 1. Can you please verify, everybody? If anybody has any question, then please feel free to ask. These are the two children of a binary heap, complete binary heap. Now, if I ask you, who is the parent of node n? Let us say I have, when my n is 3, the parent is 1. When my n is 4, the parent is 1. In general, for any n, what is the parent? Floor of n minus 1 divided by 2. Very good. Good answer. So it is the floor of n minus 1 divided by 2. You can verify it. Floor of n minus 1 upon 2. You can verify, put n equal to 3. You get 3 minus 1 is 2, 2 upon 2 is 1. So floor is also 1, 1. And when n equal to 4, 4 minus 1 is 3, 3 upon 2 is 1.5, floor is 1. Similarly, verify for 5 and 6. You can easily verify. Okay, so this was also a good exercise. So now, if I ask you, who are the children of this node 3? Oh, it's not there, but okay. Who are the children of 2? You immediately know 2n plus 1 and 2n plus 2. So it's 5 and 6. These two are the children. So in this way, this complete heap can be implemented with an array. Now, Ali Faraz asked one question. How do you know which is the next unfilled node? So you can see in an array, it is very easy to find what is the last entry of the array, right? So this is the last entry of the array. This is the last filled node. And if I add one more entry into this array, then that will be the next node, right? Okay, so I think this was all about heaps. Now we have to come to the implementation in a code. So, okay, how do we implement a heap in Python? Okay, so my whole purpose of doing this exercise now is to make you comfortable with how you implement the whole thing with classes. How do you define nodes? How do you define relationships between nodes? How do you define operations on those nodes? So that is why I'm going to discuss the details of this implementation. Okay. So I can define a class called complete binary heap, right? In this class, I have data, which is basically just a linear array. It is simply a list in Python. So when I initialize my heap, it is simply an empty array. It's an empty list. And the indices are I, and data underscore I is the value or the data at that index. Okay. Now, first thing you want to see is if I have a heap, can I print it? Can I see what are the values? Can I print the whole structure? Just like we saw in our drawings, we can draw, but similarly, can the computer draw it for me? So printing is a very good operation to start with. How do I print? Okay, I have written a very, very simple implementation, but I would suggest you print it properly if you want to. Okay, so one very simple thing you could do is you can print it simply the array. Like this command will simply print the array, right? What is my array? My array was simply whatever it is, 2, 5, 9, etc. It is simply printed as an array. But if you want a better printing, you can print it like this: 2, then 5, 9, then maybe 10, 12, 16, 14. This is what this part will do. But still it is not very pretty. So if you want to print it even prettier, you can use pydot library in Python, which basically will print it like this. So 2 is there, then 5, then 9, then 10, 12, okay, basically 16, 14. Okay, so yeah. Okay, now let's come to the operations which we just now discussed. How do you add an element? Okay, I've just written on top of on the top the example that this is a linear array. The data is there, and then the indices are here. How do you add a new element? So first thing I will do is I will create an just a moment. I will create an array. Sorry, I will create a function for that operation, right? That is, I will create a function that I want to add some data D. Let's say I want to add 10 into this heap. So D is 10 here. Now, this function, what does it do? First of all, what was the first thing you do? You add that entry at the next vacant node. So basically in this list, I'm just appending 10, right? This means my 10 comes to the index 7 here, appending. And then what do? You have to bubble up, right? What you have to bubble up? Bubble up the last node. The last node you have just now added. What is the last node? It is simply the length of the array minus 1. So now the length of the array will be 0 to 7 means 8 minus 1 is 7. So this will be the last node. The index of the last node is basically 7. And I give this index and create a new function called bubble up. This is a general function. Basically, starting from the given node, it can bubble up the values to the root. That is a new function I have created called bubble up. Now, okay, I have to implement this function. So, okay, whenever you write a program, it is good that first you create an abstract function. Okay, assume that this function exists and write your code, complete your current function, and then you write the new functions. For example, in this, for adding an element, I need to create a function called add data, and I will write down all these things as if I have these functions available. Like I want to get hold of the last node. I don't have that function, but assume that it is there. Define the input output pair for this. Similarly, bubble up. I don't have this function implemented yet, but assume that it is existing and complete this function and then implement this part. Okay. So now come to now I have written this function. This function is still not written. So I have to write this function called bubble up. Okay. So what do I do when I do bubble up? I have to bubble up starting from node I. It could be any node. I'm not saying it's the only last node. It could be any node I, and I have to bubble it up. You remember in the operation of removal, when you are removing somewhere from the middle, then when the new entry comes, you have to bubble up from the middle also. So it is good idea to bubble up, to write a general function which can bubble up from any node. So my node is I. Now I have to do bubbling up operation. And so you compare with the parent, right? And if the heap invariant is satisfied, you stop there. If the heap invariant is not satisfied, you swap, right? So that's what I'm doing here. So first of all, get hold of the parent. Okay, given this node, who is the parent? What is the index of the parent node? We just computed in the previous slides. The parent is n-1 divided by 2 floor, right? So we don't have this function implemented yet, but assume it is existing. Write it down somewhere that, okay, I have to implement it later and then complete this function. So, okay, this function returns the parent of the given node. Now I will compare the current node with its parent. Is the heap invariant satisfied or not? Now, to do this comparison, I have created another function. Assume that this function is existing, which is just finding the heap invariant property. And if this heap invariant is satisfied, then I break, means I don't bubble up further. I will just stop here. And if it is not satisfied, then I swap the data. I swap the data. So I don't have this function, but okay, assume it is existing, write it later. Now, note one thing, that is heap invariant. I could have simply done a comparison of data, right? Parent and node. But then I want to leave it general, that heap invariant, I want to define it as a general function. Okay, for example, tomorrow I want to create a max heap instead of min heap. I just change this function, everything else remains same, right? So that is why I want to write, I'm writing it in a general way so that it can be used for both min and max trees. Okay, so this is, now remember we have written some functions here. First is get parent node. Let us see how we implement that function. You have already done it, n minus or I minus 1 upon 2 floor, right? Then I have to implement the heap invariant function. What do I do here? Okay, heap invariant is a function. It is a function of parent and child. The indices are given. Now I will get the value at this index, right? Get data. Now get data is another function, which is basically, it goes to data underscore I basically just gets the value. And for the child also you get the value and compare them. If it is, if this condition is satisfied, it returns a true, otherwise it returns a false. And if it returns a true, this means heap invariant is satisfied and you can stop bubbling up now, right? Otherwise you swap the data. What is the meaning of swap the data? You have these two nodes, ith node and jth node. You have to swap their data. So what will you do? It's just simple operation, create a dummy placeholder where put the ith node data here and then put the jth node data on the ith node and then put this data in the jth node. Like, okay. So now, similarly, you can also define bubbling down operation. Just like you have bubbling up operation, you can also have bubbling down operation, which I am defining it in this way. Same thing, that now you have to get the child. So you get the elder child, or get the child which is smaller in this case, basically which satisfies the heap invariant. So get the elder child, which means the value one with a smaller number, and then again do the comparison. If the heap invariant is satisfied, break it. If it is not satisfied, swap the data, right? And then make the node as, make the child, means take your pointer to the child now, and then again repeat this operation until this loop is finally complete. So, okay, what is the get elder child? Basically the same thing. You compare the children, and whoever is a smaller child, that is returned. Okay. Okay, now, okay, get child node. Okay, so basically get elder child needs all the nodes. So you are here returning all the nodes. What are all the nodes? It is 2i plus 1 and 2i plus 2, right? Now it is possible, like if you remember in the previous example, if I say 6, what are the children node of 6? Then those nodes are not existing in the tree, in the heap. So what do you do in that case? You will simply say, if my length, okay, my children, this minute, get child nodes. Yeah, get child nodes. If my child node is, if my 2i plus 2 is less than the last node, then only you can return. But if it is larger than the last node, then you return an empty array. I think this you can manage. Now come to the polling operation. So what is polling operation? Removing the topmost entry. So it is simply a function, poll data. So what you do, you get the data at 0th node, right? Get data at the 0th node, and that value is returned, and then you have to remove that node, right? For removing, you create another function, remove node, and then you, what is the meaning of remove node? Remove the node, you remove that node, swap the data with the last node, delete the last node, then bubble up and bubble down, basically both the things, bubble down and bubble up. So if bubble down property is already satisfied, then you just don't do anything. Then bubble up property is satisfied, then you stop. Okay. So, okay, this was the whole thing, the implementation. Now come to complexity analysis. We have already done it. Adding a node is order n, order log n. Polling is order log n. But removing a given element is order n, because my search is a costly operation. Now, is there a way we can make the search efficient here? The answer is yes. We can make our search efficient with the help of hash tables. What is a hash table? In simple terms, a hash table is something like this. If we can map, okay, first in terms of heap, if I can map the value to the node index, for example, if you tell me in this case, if you tell me 3, right? If I have a black box function, given 3, it can tell me what is the position of 3, what is the index of 3. That is a hash function. Given 3, it can immediately tell me, okay, 3 is at position 0, 1. 3 is at position 1. If I ask it 8, the input is 8, the output is what? So 0, 1, 2, 3, 4, 5, 6, 7, 8. Okay, it's also 8. So somehow by chance it is also 8. And if I say 13, so that hash function will return 0, 1, 2, 3, 4, 5, 6, 7, 7. So hash function will return 7 immediately. If I can maintain a table like this, right? Or a function, a magical function, basically it is a table like this. So 2, the value 2 is stored at, okay, if there are repeated values, that also can be taken care of. The value 2 is stored at index 0, index 2, index 6. Value 7 is stored at index 1 and index 4. Value 11 is stored at index 3, 13 is stored at index 5. This is like a hash table. But in general, hash table is basically simply a mapping from a key to a value. Python dictionaries, you have used Python dict, that implements a hash function. So you given any key, it maps to the appropriate value. Basically, it maps to an index, and that index is the value. Okay. And if you want more details, you can go through this blog or write up on this tutorials point to see what is a hash function. This figure is from there. A very simple explanation of a hash function. Just like in Python dict, you have keys, you give the key and you get the value out. How the hash function is implemented is a separate topic. We are not going into details of that, but for you, you can use simply Python dict. That is the hash function. That implements hash function. Okay, now we are maintaining a hash table. So as I told here in this slide, that we have got this heap and the corresponding hash function is this. Now let us say, okay, actually this part was there. This was the original heap. Now I want to, now if I am maintaining a hash table, then I also have to modify my hash table whenever I modify my heap, right? Remember all those bubbling up, bubbling down operations that will not only change the heap, but also the hash table. So you have to simultaneously change that as well. See, there is a cost somewhere involved. The moment you say, I want to make my search efficient, you have to pay in every operation. You are adding number of steps, means number of operations in each operation. So earlier the bubbling up and bubbling down were simply you are modifying the heap, but now you have to also modify the hash table side by side to maintain the heap invariant in both the tables, or in the heap as well as the hash table. Okay, so how do I do adding an element operation? So I have an element, I am adding a new element 3. So I will just add it here. Basically in the hash table also I add it at position 7. This is the first thing. Next thing is I have to do bubbling up and bubbling down. What is the meaning of bubbling up? This 3 will go to 11. It will swap with 11. So when I do this swap, I also have to swap here. So here also 3 will come here, 7 will go there. Basically now 3 is at index 3, right? And 11 is at index 7. And similar, and then again up, then 3 will go to 7 with this position, 3 will go to 1, and this 7 will come to index number 3. So finally it will like this. So 3 has reached here, 7 has reached here, 11 has reached here, and accordingly side by side you have swapped in your hash table also. Now 3 is at entry 1, 7 is at entry 3 and 4, 11 is at entry 7, node index 7. Is it clear? Does anybody have any questions at this point? Okay, good. So, okay, so you may not use heaps frequently in your in your course, in this course also. But why we did this exercise, the purpose was this, that how do we write functions to implement what we want to implement, right? This was an exercise which I wanted you to go through to be able to write programs which can do what we desire. Okay, now let's come to the next topic. It is called sets. You know sets are always very common in any operations which you do. For example, you are doing some data processing and you create sets, you create like, you know, in clustering you have to create sets, right? They are sets. And when you do, yeah, clustering is one thing. And when you do some kind of segmentation, let's say image segmentation, there also you are maintaining sets, right? This is one segment, is another segment, and then your segments are increasing or decreasing. Yeah, so sets are very useful in different machine learning aspects. Okay, now first let us go with the very basic definition of sets. Sets are basically entries. Basically a set is a collection of elements, collection of items. So a set A has collection of items 1, 5, 8. B has collection of items 2, 5, 6. And then I can have operations like union. Union of these two sets will give me the total number of entries. intersection will give the common elements, and difference will give the elements which are here but not here. Oh, yeah, sorry, the elements which are here but not here. Yes. Okay. So how do I implement sets in Python? In Python has a its own set function. This is a set data type basically. Python has its own implementation of set data type. To define a set, you write it like a list, but instead of square brackets, you put curly braces. Instead of square braces, you are putting curly braces. That is a set. So A is a set, B is a set, and A union B. So union is an operation on this set. So it is, and if you want to see more methods, the union, difference, etc., then this is a nice place where you can get these W3 schools. This page has list of all those operations, and you can, it's very simple, just go through it. Now I will go through one simple algorithm called which uses these set operations. There are still 10 minutes to go, so I will complete it. Okay, let us say, okay, now what is a graph? A graph is some vertices and some edges. So like A, B, C, D, E, F, G, H, I, J. These are the vertices or the nodes or vertices, and they are connected via edges. This is one edge connecting A and G, another edge connecting C and G. These are all edges. Now, what is a minimum spanning tree? It's another term. Minimum spanning tree basically is a subset of edges that connects this subset. It connects all the vertices. All vertices are connected with minimum total edge cost. So I want to find a subgraph which has got all the nodes connected, but the weight of each edge is the minimum. Okay, so every edge has got a weight, right? These are weighted edges. And I want to find a subgraph which has got all the vertices, but only a subset of edges, and such that my total edge weight is minimum, total edge cost is minimum. That is called minimum spanning tree. Okay, it may not be unique. There could be multiple answers, but okay. So is there an efficient algorithm to find minimum spanning tree? The answer is yes. That algorithm makes use of set operations. Okay, if you know hierarchical clustering, that also makes use of similar set operations. Okay, so this is like a hierarchical clustering. How do we go about it? It's called Kruskal's algorithm. It's a very popular, it's a very famous, efficient way to do this kind of clustering. So you have, first of all, you sort all the edges by ascending the edge weight. Like put it in an ascending order, like because you want the minimum ones. So let the minimum ones be at the top, and then the bottom is the larger weights. Now you pick the first edge, like go over all these sorted edges. Take the first entry, which is the smallest weight, right? And get the vertices of this edge. Like let's say, let me do it with an example. This is an example here. Okay, let me just copy. Okay, so what does it say? First of all, sort all the, oh, maybe I think let it be here only. So first, okay. So first of all, create a sorted list. Okay, I will create a sorted list of this. I will say the sorted list is like this. My A to B has a weight 1, and then CG has a weight 1, Nobody else with 1, with 2, GD with weight 1. Sorry, with weight 2, sorry. And what else? No other 2. Okay, 3, DF 3. Like that, you create the entire sorted list. Next is you go over these and take an edge, the smallest edge, look at its vertices. So let us say, so take the smallest edge, okay, the smallest edge, this one, A to B. So this is smallest edge. What are the vertices? A and B. Okay, I got the vertices A and B. Now, if the vertices are in the same set, then continue. If the vertices are not in the same set, then unify them. And if all the vertices are unified, then you can break this operation. What do I do? So A and B are not in the same set. In the beginning, everything is segregated. It's hierarchical clustering or it's agglomerative clustering. Everything is first separated. And you first have to see A and B, okay? A and B is not in the same set, so you can link it. You connected it. You took it. You take it. Next, go to the next one. C and G. Are they in the same set? No. So okay. So now these two are in the same set, and everything else in the different sets. Connect these two. Now these two are also, they come to the same set. Next, go to GD. Is it in the same set? No. D is in a separates. It's a standalone item and a lone item. This also form the link. Then actually I can draw with different colors, but okay, leave it like this. Okay. Now D and F. So this is the next entry. Are they in the same set? Answer is no. D is in this set, but F is separate. So okay, combine the two. 3 is done. Now 4. G and F. Are they in the same set? The answer is yes. They're already in the same set. So don't link them. Don't take this edge because the vertices are already in the same set. Right? These are all in the same set. Now, go to the next one. 4, AD. Are they in the same set? No, they are in the different sets. Okay, so link them. So now they are in the same set. Now go to 5. 5 again, these are in the same set. So no. 6, they are already in the same set. Don't link them. 7, they are in different sets and link them. Now all the elements, all the nodes are in the same set. So now we are done. We can break the loop, right? Now all the vertices are unified. You can break the loop. Okay. Well, this is the Kruskal's algorithm. Now, how will you implement it, right? To implement the Kruskal's algorithm, first of all, consider what all entries do you need. This is the algorithm. I have written it here. What all entities do you need? Entities are the vertices and the edges. This is the graph. And then you also need to keep track of the sets. Like in the beginning, all of these were in the different sets. Like we had how many? 1, 2, 3, 4, 5, 6, 7. 7 different sets were there. But slowly, number of sets kept on decreasing and decreasing. Ultimately, we were left with only one set. Okay. So we need all these 3 entities. Now, what all operations do we need? Because those are the operations which we want to make very efficient. Okay. First operation is given the edge, I should be able to find the vertices, right? Given an edge, I should be able to find vertices. So I need to write a function called get vertices for a particular edge. This is one operation which should be done efficiently. And the other is given a vertex, I should know what are the whether they belong to the same set or not. So I need an operation vertex to set. If I implement set to vertex, that will be inefficient because that is not what I need for this algorithm. I need vertex to set. So maintain your hash table in that way. Okay, so there is a comment here. won't we also need to consider the A to D edge to unify C, G, D, F, and AB sets? Yes, we have considered A to D edge. It is there. A to D edge is there. Okay. So, okay, so I think that is it. It's almost 6:30 and we are we have discussed today about heaps in quite some detail, and then sets also in we saw the Kruskal's algorithm for minimum spanning tree, uh, which is like hierarchical clustering, agglomerative clustering, and how we implement it very efficiently with the help of sets. Okay, any questions from anybody?
Sir, it looks like greedy search algorithm. Will it be optimum?
Which algorithm?
Sir, we have like taken these edges 1, 2, 3, 4 in the ascending order. So this looks like greedy search algorithm. Will it be the optimum one?
Um, in this case, it turns out to be optimal. Can you think of any situation where it is not optimal? Good question. Good question. Think about it a bit more. Can you think of a situation where it is not optimal?
Like I have seen some graphs where, let's say, if we have to go from A to F, then there are alternate paths as well, which ultimately comes out to be the total sum is less than as compared to this greedy search. So that I have seen in some books. Like,
Okay, maybe you find that example and send it to me, and we can discuss in the class.
sure, sir.
Okay, if you can create a graph which is not optimal, where this minimum spanning tree is not optimal, this Kruskal's algorithm is not optimal. Okay, good question. Thank you. Okay,
Sir,
yeah.
sir, do you start the class at 5? Or because when I joined at 5, uh, 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 sorry, 5:10. When I joined at 5:10, it was already on. The class was on.
I started around 5, 6 or something. Okay,
Okay, fine.
next time I will
So,
start 5:10 then, because yeah, I think okay. I will
I think
start
the
at
official time is 5:15, but if you want, you can take that time. I'm not saying that you shouldn't take that time, but
okay, okay.
just inform everyone so that we can join at the right time.
Okay. I'm sorry. Yeah, okay. Then I will start at 5:15 next time. Next time we will start at 5:15 and end at 6:30. Okay.
sir,
Sorry, but you can watch this video with the portion you missed in the YouTube. Yeah, Jayant.
sir, regarding the greedy uh, problem that was mentioned earlier, for example, in the same example, A to E, node A to node E will take 9 if we go through B.
Node A to E.
E. If we go through B, it will take 9 units of uh, work or whatever. But if we go through the minimum spanning route, it will take 4 plus 3 plus 7, 14.
Hmm. Okay, good question. So the goal here is not to minimize the path distance, but the goal is to find a tree which spans the all the nodes basically, of all the vertices with minimum weight, right?
Okay, sir.
It may not be optimal in terms of path length between two vertices, but it is optimal in the sense that the overall weight is minimum.
Sir, so this is not like one of those network problems in which we look at best optimal path for packet traversal or anything.
No, it is not that problem.
Okay, sir.
Okay. Yeah, thank you very much. We can stop here. If you have further questions, you can ask in the next class or you can ask on the Mookit portal. Thank you.
Thank you, sir.
Thank you, sir.
Thank you. Bye.